Welcome to our video on the simulation of a cantilever beam for mechanical engineers. Cantilever beams are an essential component in many engineering designs, such as in buildings, bridges, and aerospace applications. Understanding the behavior of these beams under different loading conditions is crucial in optimizing their performance and ensuring their safety. In this video, we will take you through the basics of modeling and simulating a cantilever beam, including the mathematical equations involved, material properties, simulation software, and the significance of simulation results. By the end of this video, you will have a solid understanding of the simulation process and its importance in the designing and analyzing cantilever beams. So let's get started. So what's a cantilever beam? A cantilever beam is a type of structural element that is supported at only one end and free to move on the other end. The term cantilever comes from the French word canton, which means corner or edge. The beam is typically rectangular in shape and its length is greater than its width or thickness. Cantilever beams are commonly used in real-world applications across different fields of engineering. For example, in civil engineering, cantilever beams are used in the design of bridges, overpasses, and buildings. In aerospace engineering, cantilever beams are used in the design of aircraft wings and tail structures. In mechanical engineering, the cantilever beams are used in the design of components such as brackets, supports, and fixtures. Here is a diagram of cantilever beam. As you can see, the cantilever beam is supported at one end, called the fixed end or the support, and is free to move on the other end, called the free end or the tip. The beam is subjected to an external load represented by the arrow, which causes it to deflect downwards. The deflection of the beam is proportional to the load applied and depends on various factors, including the beam's material properties and dimensions. To simulate a cantilever beam, we need to develop a mathematical model that represents its behavior. The model typically consists of a set of equations that describe the relationship between the different parameters involved in the system. Here are the key components of the mathematical model for a cantilever beam. The governing equation for cantilever beam is Euler-Bernoulli beam equation. This equation relates the beam's deflection to the bending moment, the beam's stiffness, and the distance from the fixed end. The equation can be expressed as follows. For the governing equations, we need to apply boundary conditions that represent the fixed end and the free end of the beam. The boundary conditions for cantilever beam are: number 1, deflection at the fixed end is 0. Number 2 is bending moment at the fixed end is 0. And the third is bending moment at the free end is equal to the applied load times the length of the beam. Now there are some assumptions that we take to make the model more simple and more tractable. We typically make some assumptions about the beam's behavior. Some common assumptions made in the cantilever beam modeling include: the beam is made of a homogeneous and isotropic material. The beam is loaded in a linear manner. This is the most important thing. The beam is subject to small deformations and is in the linear elastic range of its material behavior. By using this mathematical model, we can simulate the behavior of a cantilever beam under different loading conditions and analyze its response in terms of deflection, stress, and other parameters. The material properties of the cantilever beam have a significant impact on its behavior and response to external loads. Some of the key material properties that need to be considered when designing and simulating cantilever beam are Young's modulus. This is a measure of a material's stiffness or ability to resist deformation when subjected to an external load. It is expressed in the units of stress divided by strain. A material with a high Young's modulus will be stiffer and more resistant to deformation than a material with a low Young's modulus. Poisson's ratio. This is a measure of a material's ability to deform in the lateral direction when subjected to an external load in axial direction. It is expressed as a ratio of transverse strain to the axial strain. A material with low Poisson's ratio will tend to expand more in the lateral direction when subject to an axial load. The material properties of the cantilever beam determine its stiffness, strength, and deformation characteristics. For example, a beam made of a material with a high Young's modulus will require a greater external load to cause a given amount of deflection than a beam made of material with a low Young's modulus. Similarly, a beam of material with a low Poisson's ratio will tend to expand more in the lateral direction than a beam made of a material with high Poisson's ratio. It is essential to understand the material properties of the cantilever beam when designing and simulating its behavior. Without accurate knowledge of these properties, it is impossible to accurately predict the response of the beam to external loads, which can lead to catastrophic failure or reduced performance. Therefore, it is critical to use accurate material properties in any simulation of cantilever beams. Boundary conditions are the constraints placed on the cantilever beam to simulate its interaction with the real world. The two most common boundary conditions for cantilever beams are fixed end and applied loads. A fixed end condition occurs when the beam is attached to a rigid structure, preventing any movement at the end. An applied load condition involves a force or moment applied to a beam at a certain point. Correctly applying a boundary condition is critical for accurate simulation. Incorrectly applied boundary conditions can lead to inaccurate results and may cause the simulation to fail. For example, an incorrect fixed end condition could result in unrealistic bending or shearing of the beam. It is essential to understand the impact of boundary conditions on simulation results. The correct application of boundary conditions allows engineers to analyze the beam's behavior under real-world loading conditions accurately. Examples of how boundary conditions can affect simulation results include changes in stress, deflection, and deformation. Understanding how different boundary conditions affect simulation results is crucial for accurate analysis and optimization of cantilever beams. Simulation software is an essential tool for designing and simulating cantilever beams. There are several software packages available that can be used for simulating cantilever beams, and some of the commonly used ones are ANSYS. This software package is widely used in the engineering industry for finite element analysis. It offers a wide range of simulation capabilities, including structural analysis, thermal analysis, and fluid dynamics analysis. SolidWorks simulation. This software package is a popular choice for simulating cantilever beams. It offers a user-friendly interface and allows for quick and accurate simulation of complex geometries. Console multiphysics. This software package is known for its ability to model multiphysics problems such as fluid structure, interaction, and electrostatics. It can be used for simulating cantilever beams with complex material properties and geometries. There are other software packages as well, like Abacus, which can do the same thing. We will be focusing on ANSYS in the following video. A simulation software works by creating a virtual model of the cantilever beam, which can then be subjected to various external loads and boundary conditions. The software uses the mathematical equations governing the behavior of the beam along with the material properties and external loads. To simulate the response of the beam, some of the features offered by simulation software include meshing. The software divides the cantilever beam into smaller elements or meshes to solve the equations governing the beam's behavior. The second is solving. In solving, the software solves the equations governing the behavior of the cantilever beam to determine its response to external loads. In the visualization step, the software will provide visualization tools to display the results of the simulation, such as stress, strain, and deformation. To demonstrate how to set up a simulation in the software, we will show an example of how to use ANSYS for simulating a cantilever beam. We will start by creating a 3D model of the beam, defining the material properties, and applying the external loads and boundary conditions. Then we will show how to run the simulation and analyze the results. Now let's go to ANSYS workbench to do the simulation of the cantilever beam